Okay, so it is our great pleasure today to welcome the scientific director for nanophotonics at Birck Nanotechnology Center. Vladimir Shalaev is really famous. He's a distinguished professor at electrical and computer engineering at Purdue University. He has done fantastic work on nanophotonics, plasmonics, optical metamaterials, quantum photonics, many other things. And Vladimir is going to talk today about this fascinating topic of hybrid quantum photonics empowered by metamaterials and plasmonics. Vladimir, the floor is yours.
All right, well, let me start with thanking Bogdan, actually, and other organizers to meet at least my old friends. And I see some of them, like Graham Milton, didn't see him for a long time, Dimitri Green, John Page, very nice, well, meet you, and some others, of course. What I'm gonna discuss today is we all indeed witnessing new technology evolution, which is quantum. And I tried to relate this technology and science evolution in quantum to the field of metamaterials, which is the subject of this workshop. And in my opinion, there is a niche where metamaterials and the ideas developed in this field actually could make a big difference for the field of quantum. And that's what I'm going to focus on. So here is the outline. Basically, I guess there are three main messages in my presentation. First, plasmonics and plasmonic metamaterials have this unique capability of confining electromagnetic modes down to nanoscale. And by doing so, they could dramatically speed up quantum processes through Purcell enhancement, to the extent that these quantum processes become faster and outpace decoherence processes, which is a stumbling block for all quantum applications. And that's perhaps the main take-home message, that plasmonics could help to solve the problem of how to keep this quantum superposition by making processes much faster. So the other obvious things, but not developed at all, in quantum, we have to deal with exceptionally small signals, like single photons or pairs of entangled photons. And ideally, you would like to have like a circuitry with a million of elements. And there is no way to develop and build such a system without machine learning. And I may make a big point on that machine learning actually enables quantum photonic circuitry. And the final point is that with our recent discovery of single photon sources in a technologically important silicon nitride platform, there is a good chance to develop for real this quantum photonic circuitry with this CMOS compatible and beloved by industry material platform. So that's the things I'd like to focus on. And let me start with this, if you wish, propaganda slide, which basically shows how calculations per second per $100 evolved with time when people came up with more and more sophisticated machines, starting with an analytical engine, going to nowadays nanoelectronics-based computers. And I guess by now, no one would argue that the next progress would be in the field of optical and or quantum, most probably both quantum and photonics, because that's where you could get really high speeds and broad bandwidths. And that's where these plasmonics and plasmonic metamaterials come into the game. And let me just refresh your memory and say a few words what the plasmonics is about. And I should say that plasmonics is an old field, but I would argue that things which I'm describing today might be the biggest potential application for the field of plasmonics. Anyway, so if you have a small particle like the one shown here, if you somehow displace electrons so that you have excess electrons from one side and excess and more positive charges on the other side, clearly they would be restoring force which would make electrons bounce up and down at the frequency corresponding to so-called surface plasmon resonant frequency. There are all type of ways to excite these plasmon modes. And if you want to speak of if you would like to accomplish the highest possible confinement, in the case of the sphere, the confinement will be dictated by the size of sphere, which could be, let's say, 10, 20 nanometers. But if you go towards so-called gap plasmons, in this case, you have a dielectric gap between two metallic structures supporting this free electron oscillation. Then such gaps could be exceptionally small, few nanometers, 1 nanometer. And that's actually enables record-breaking confinement of electromagnetic modes. And that's the thing which I'm going to use to speed up quantum processes. Interestingly enough, the field of plasmonics was first developed for rather complex systems, random systems, which often have fractal morphology for the reason that they grow this way. And fractals are actually structures that reproduce the morphology, the geometry of the whole structure on a progressively smaller scale, like either deterministically, like in the case of this form, you could see that the structure of the whole is repeated on this scale and on this scale and so on and so forth, or statistically on average, like in the case of this fractal aggregate of silver colloidal nanoparticles. And as we showed in our early works, actually long ago, that fractal morphology promotes localization of these collective plasmon excitations. Each small particle support these plasmon oscillations. Of course, they couple each other. You have this formation of collective modes, and it turns out to be they are localized in very small nanometer scale areas, which we refer to as hotspots. And in these hotspots, the field, local field intensity, could dramatically be much higher than the field intensity of incident light, simply because you basically have this accumulated energy in the course of time. And the most important thing which relates to the field of metamaterials is the fact that in these random composites, properties are defined by structure and geometry. And that's very similar to later developed metamaterials. And in that regard, you could say that random composites actually serve as a precursor to the field of metamaterials. And since we mentioned this field of metamaterials, let me show some results, which of course show the power of this artificially designed and engineered materials to do quite miraculous things, including particularly for this 2D version of metamaterials, which are called meta surfaces. Like in this case, you have a meta lens or a meta hologram. And the thing is that they could be much thinner than the wavelengths. With conventional optical elements, you accumulate the needed phase by controlling the thickness of your bulk optical element, like in the lens. Here, you do it abruptly, change the phase by using these plasmonic nanoantennas, which could be much, much smaller than the wavelengths. And of course, with metamaterials, it's becoming now real thing in the field of optical. So there are companies which develop all these meta lenses, meta holograms, glasses, and many other things. And in principle, it could do really very nice things, such as even these non-reciprocal devices, as I showed here, which is like a holy grail for nanophotonics. So, but my talk is largely about quantum and what plasmonic metamaterials could do for quantum. So, speaking of quantum, where, as I said, basically the next technology revolution is going on, there is no really actually a simple solution in terms of the material platform to use. Clearly, there is a trade-off between interaction strength, where superconducting qubits seem to be most promising, and the coherence time, where photons are probably unbeatable. And there are many other platforms in between, such as those based on the various color centers in diamond and other structures, rare earth, trapped atoms, trapped ions. So I guess the most probable answer would be that depending on the functionality, quantum functionality you would like to accomplish, that's going to be a hybrid platform. But that's what most of groups now are working, trying to find out most suitable materials for various quantum applications. One thing is obvious, though, that photonics would play a central role in future quantum technologies. After all, with photons, we package information into signal of zero mass and propagate it the ultimate speed, which is speed of light. So clearly, photonics would play a central role in quantum sensing, quantum communication, quantum simulation, and most importantly, quantum computing. So here I'm showing just as an example this quite spectacular quantum communication enabled through satellites, work done by the Chinese group led by Pan. And so in this case, they realized this communication was thousands of kilometers. But if you look at the speed, the rate with which this communication, because it's quite low, kilobit per second. And this is because the very fundamental problem for light-matter coupling. So of course, photons are robust, and the reason they are robust, they don't couple to each other, and they couple very little to matter for simple reason that light wavelengths is much larger than the size of any quantum units, qubit, atom, whatever. Because of this size mismatch, the coupling is typically small, and that's why actually photonics is robust. However, this is a double-edged sword. To control generation of photons, to reroute them, to control them, you actually need to have this strong coupling, like matter coupling, but you would like to have it on demand. So basically switch it on and switch it off. So, and that's actually the area where plasmonic metamaterials could play a very essential role as far as I see it. So let me remind you what plasmonics is unique about and what it could do for quantum photonics. Let me start with this experiment we did some time ago in collaboration with ETH, with a group led by Jörg Leuthold. So it just shows that you could have this ultra-fast plasmonic modulators. The idea is very straightforward. Let's say if you have this gold ring resonate, as it's shown here, and in the gap, you fill it with the electro-optical organic material, which changes its refractive index when you apply voltage. And if you say a signal or the silicon waveguide shown in blue, so if light in the waveguide doesn't couple to this ring resonator, it goes without any loss, it simply goes through. However, if you apply voltage and change the refractive index of this ring resonator so that now that light couples to the ring resonator, then it doesn't go through simply because it couples to the ring resonator. So you could switch it on and off, and it turns out that the speed with which you could do it actually in the terahertz range. And this is the very essential thing about plasmonics. Plasmonics could enable ultra-fast operation. And that's exactly the point of its applications for quantum as far as I see. This conceptually perhaps the most important slide for further understanding of my lecture. And this is about enhancing light matter coupling. How can we enhance it? It's well known actually how. It was suggested by Purcell, who, by the way, graduated from the same department where I have honor now to teach. So he is from Purdue University. Anyway, so if you place your qubit, or let's say atom, inside of a cavity, then photon, despite the fact that it has the wavelengths much larger than the size of this atom, would bounce many times between the two mirrors and effectively would couple stronger to your qubit. And the enhancement, because of this, which is called Purcell enhancement, is given by this ratio of quality factor of your cavity divided by the volume where your electromagnetic mode confined. And most of the group, and this is quite natural, go this way that they take the electric cavities with as high possible quality factor as high quality factor as possible. For example, using these defects in photonic crystals. In this case, Q could be spectacularly high, like 100 million, but volume still is diffraction limited, so it cannot go below the wavelengths. And we think to emphasize here that you pay the price yes, you do have increased light matter coupling, but the larger the quality factor Q, the slower the response. You know that quality factor is inversely proportional to the width, so and the width is very small, it means that the response is very slow. So could we go the other way without sacrificing the speed? And that's exactly where plasmonics comes into the head. At hand. So why, if for plasmonics, quality factor is relatively low, 100, but the volume could be exceptionally small, as I pointed out, like let's say 5 nanometers. 5 nanometers is 100 times smaller than the wavelengths. So you have to raise it to the power 3, which gives you 1 million. You get increased by factor of million only because of this exceptionally small confinement of electromagnetic mode, exceptionally strong confinement of electromagnetic mode. And quality factor Q100 means that it's additional enhancement. So you end up with the same number, the same enhancement. But in this case, because Q is only 100, it means that the response would be the terahertz range. So basically it will be broadband system. So if the, let's say the carrying frequency 10 to the 15, Q on the order of 100 means that you move to the terahertz range, and that means that the response would be with picosecond times or sub-picosecond time. And that's exactly what you want. In this case, you have a strong light matter coupling, but the system operates at very high speeds, potentially at speeds that overcome the rate with which decoherence occurs. And that's what we would like to address. And this slide illustrate this idea. Normally, to beat this problem of quantum decoherence, people go to all these extremes, going to exceptionally low temperatures, low pressures, trapping atoms or trapping ions. So in that, what it does, it increases this the coherence time. So it becomes longer living this coherence time. What if instead of going this way, I simply speed up the process? Let's say it could be any quantum mechanical process, but to be specific, let's consider single photon emission. So what if I place my single photon emitter in a plasmonic cavity so that the emission would occur in a very fast fashion, which faster actually than the decoherence happens? Then basically my system would be decoherence free because a photon would be emitted before decoherence happens. And it means that it would be actually immune to quantum decoherence. So that speed up enabled by plasmonics is unique and could be actually one of the most important applications of plasmonics or plasmonic metamaterials, because when you make these structures, you have like meta surfaces, so all these type of structures which belong to the field of metamaterials. So that's the idea. So, and to illustrate this idea, let me show some of our initial experiments. We, of course, keep working in this direction. So let's consider a specific example of so-called nano-patch antenna. So in this case, you have epitaxial silver, and silver is exceptionally good plasmonic material, and single crystal silver cube. And if you place in between the cube and the film, epitaxial film, let's say quantum emitter, like in this case, nanodiamond with a single nitrogen vacancy. So then this emission, spontaneous emission, would be enhanced through this gap plasma. So what you need in this case from your nano-antenna is actually two functions to accomplish. You would like to have the gap as small as possible. The smaller the gap, the smaller the volume, the stronger the per cell enhancement, the stronger increase in light matter coupling. But it's important also, the gap should be small, but the antenna itself should not be too small, because you need to outcouple these single photons. And the rate with which you outcouple depends on the volume of your antenna. So it turns out that the optimal size is in the range of, let's say, 80, 100 nanometers. So then ideally your system would operate in such a way that your photon would be emitted before decoherence happens, meaning that it would be immune to decoherence. And it could be also faster than any loss happens. So meaning that your plasmons do not have enough time to decay. So it would be loss-free, decoherence-free outcoupling of single photons. And this all calculations and preliminary results show that it's quite doable. You just need this very efficient plasmonic nanoantennas. So this is a kind of first experiment. They were naive, but already very promising. In this case, we just would simply take a epitaxial silver of really high quality and just randomly distribute nanodiamond of small sizes, like 25 nanometers, that some of them have this nitrogen vacancy and could work as single-photon emitters. Then we randomly also distribute the silver cubes. And just by chance, in some cases, this single cube would find itself on top of nanodiamond, and that could work with this nanopatch antenna I'm talking about. To prove that we're dealing with single photon sources, you do this typical G2 correlation function measurement. And if it goes below 0.5, then you could say that this is a decent single photon emitter. So what we obtained with this experiment, that the rate with which single photons were emitted when they found themselves in this nanopatch antenna increased by roughly 100 times, reaching 30 million single photons per second, which is at room temperature, it's important to say. But if you take into account the transmittance of your system, which was 25%, collection efficiency 50%, and efficiency of your photodetector 70%, the actual rate with which the single photon were emitted at room temperature was already close to half billion single photons per second, which is quite impressive. And importantly, the number of photons increased by a factor of 100 times, and the lifetime decreased by a factor of 100 of times, meaning that all this enhancement goes to a radiative channel, because it could also be non-radiative, but it's clearly radiative, which is important. But that was not really that probably the best way to do it. So in following experiments, we would first place this nanodiamond on glass substrate and pre-characterize them by using this microscope and seeing which really nanodiamond is good. Then we will pick up that nanodiamond with the tip of this AFM and place it on epitaxial silver. Then the same tip would push a silver cube on top of the silver so that this nanodiamond would sit exactly at the edge of this cube, whereas calculations show per cell enhancement is the largest. And in this case, we obtained much stronger results. Lifetime shortening was 3,500, so that the lifetime actually was record short, 23 picosecond. It was actually shorter than the jitter time, so we couldn't even measure this G2 function with conventional CW lasers. We had to use femtosecond lasers, but we proved that indeed G2 goes below 0.5, so it is a single photon source. And most importantly, if you do calculations, you do theory, which was done in collaboration with Jacob Krugin, it turns out that the rate under ideal conditions, the rate with which photons would be emitted. The ideal conditions here imply that the size of the gap is 3 nanometers, the size of this cube is 60 nanometers, then the efficiency could reach 96%. It's because they just photons are not lost, neither to decoherence nor to any decay process. They emit it so efficiently out. And the rate with which single photon emitters could be emitted, ideally, it's could reach 300 terahertz. So that's quite impressive. And in principle, in this particular case, even this enhancement we obtain is not sufficient, because the dephasing time is even shorter in case of nitrogen vacancies, because very strong coupling to phonons. So we actually need to have to get a system with relatively low decoherence time, let's say around picosecond. Typical lifetime is nanosecond. With per cell, let's say 10,000, you would beat the decoherence time by a factor of 10. So, and for that, we are now looking at other type of single photon emitters, such as germanium or silicon vacancy, or HBN centers, which in this case, the gap would be even smaller and the enhancement would be particularly strong. So, and that in principle could enable exceptionally important thing, first demonstration of room temperature indistinguishable photons. I should say that, in my opinion, the most promising and probably the only fault-tolerant and scalable approach for quantum computing is photonic quantum computing. And the thing which is absolutely needed for this, it's a source of indistinguishable photons. And I think that's approach gives us a chance to succeed in this direction. Okay, so I mentioned that machine learning is very important because let me explain why and how really it could make a difference. So in the course of this identifying really good emitters, that's how actually photoluminescence map looks like. You could see there are thousands of these nanodiamonds, and we would like them to be small, because the smaller the size of nanodiamond, the smaller the gap between the cube and the silver film, and the stronger Purcell enhancement. And if you, let's say, have nanodiamond of 25 nanometers, only 1 out of 1,000 of them would have would host NV centers. So you really have to find out a good emitter. You need to characterize quantum purity to measure this G2 function, stability, brightness, and that takes very, very long time. And if, let's say, if you need like millions of single photon sources, such as needed for this photonic quantum computing, that becomes impossible without some more intelligent approach. So could machine learning help with this? So let me illustrate how it could help. So normally to do this, to characterize this purity of quantum emitter, so you do this measurement of autocorrelation function. Basically, you send 2 signals through 2 arms of correlation card and measure this G2 as a function of delay. And ideally, to get this nice gap, nice deep at delay equals 0, it takes several minutes, up to 1 hour actually, to get this nice deep. Then you fit it with this so-called Levenberg-Marquardt fitting given by this function. And when you fit it, you take the delay equals 0, and then if G2 at 0 delay is below 0.5, then it's a single photon source. Actually, the smaller the better, the higher peak quantum purity of your emitter. But it's indeed very time consuming. If, let's say, I would like to get something similar within 1 second, that's how my spectrum would look like. Clearly, you couldn't say anything about this deep, and you couldn't do any fitting. However, what you could still do in this case, you could train your neural network with emitters which you pre-characterize. Let's say you have some emitters, you know, some of them are single photons, some are not single photons, by doing these time-consuming measurements, and then you use them just for training. And when you train your neural network, then within 1 second, with very high fidelity, you actually could predict whether it's a single photon source or not. And this slide illustrates this. If we do not do this neural network training, then the probability, the accuracy with which you predict whether your source is single photon or not is 53%, which basically means it's random guess. Of course, your emitter is either single photon or not, and 53% means it's just like flipping a coin. However, with if you apply this machine learning-based training, then actually the fidelity goes above 90%. So within 1 second, just during 1 second measurement, which is nearly 2 orders of magnitude faster, you could say whether it's single photon source or not. That's very important. And you could use other metrics mentioned here, and they all look very high. So let me do more illustration how machine learning could be important. And because this is just one example, the single photon source. Let me touch the super resolution imaging. It's a very important subject. And let me just remind what is this resolution limit. Of course, it's based on some fundamental assumption. Assumption number 1, it's related to linear optics. And the resolution limit is this lambda divided by 2 numerical aperture. So that's true for linear optics. You also imply that this is stationary sample, that the illumination is homogeneous, and that you're dealing with classical fields. If you break any of these 4 assumptions, then actually you could beat the resolution limit. And some of them is well known. Like, for example, if you go from linear to nonlinear optics and apply so-called stimulated emission depletion, STEP, then in this case, of course, you could beat this diffraction limit, as was demonstrated by Stefan Hell and others. If you use also non-stationary sample, then actually this is the basis for another microscopy, which is called stochastic optical reconstruction microscopy, which enables also the super resolution. If you use inhomogeneous source, then actually that's the basis for so-called structured illumination microscopy, or SIM, which also brings to super resolution. So what about changing classical field to quantum fields? Could we gain something in that? So, and that's to explain the idea, let me just show you this Gedanken experiment suggested by Stefan Hell. So he said, hey, what we have a source of light which emits 2 photons only. So every time it emits photons, it goes by pairs. So then if I place here a 50-50 split and 2 independent cameras, that basically 2 independent Gaussian spots with the same point spread function. That simple multiplication in this case of these point spread functions leads to gain in resolution by square root of 2. And of course, in real quantum experiments, we are dealing with anti-bunch. Here, photons assumed to be emitted by pairs. In the quantum experiments, it's actually anti-bunched. So, but the statistic, the information is still the same, which implies that we could gain in resolution by applying the same idea. And this is how it works. Actually, what you do, you measure photoluminescence map, like it's shown here, like in every single spot, you measure photoluminescence. In parallel, you measure this G2 at pulse at delay equals 0 mapping. And then by correlating the two, which is equivalent to this multiplication of 2 point spread functions, you get improvement by square root of 2. And that's for in the case when you measure this correlation function of second order. If it would be, let's say, third or fourth order, then the improvement in resolution would become progressively higher. The problem, though, is that it takes very long time to measure G2, as I pointed out. And here you have to create map, and every single spot measure this G2 correlation function. So, but machine learning, again, could do it much faster. And here, what we illustrate here, this is 5-second collection time, as opposed to typical, let's say, 5 minutes or so. And this is the map of this G2 zero delay obtained by applying this neural network training. So as a result, we get this as photoluminescence map, which is of course diffraction limited. You have this G2 at 0 delay map, and correlating the two, you obtain the image with improved resolution. And because you apply this machine learning, instead of spending 17 hours to obtain this G2 map, you spend only 1.4 hours, which is speed up by a factor of 12. So to prove that indeed this is improvement in resolution, so you do this measurement of intensity distribution over the spot. For photoluminescence, it has this width, and if you do this mapping and correlating with G2 distribution, then you have square root of 2 increase in the resolution. So to sum up what we discussed so far, machine learning indeed could speed up, as we showed, by a factor of 100, classification of emitters, whether single photon or not single photon emitters. Moreover, it enables to get this information about anti-correlation function within 1 second, which is simply impossible with normal way. And in terms of super resolution, you could also get this fast improvement in resolution if you apply machine learning. Of course, we would like to take this technique to this integrated quantum photonic circuitry, which could be applied for quantum communication and quantum computing. So basically for things like single photon source emission control and optimization, to optimize cavities, couplers, frequency converters, and so on. And for this, we use some special approach, which is called variational autoencoder. In this case, the idea is that you create this so-called latent space, which compresses features from the training set to a very compact space called latent. And the important thing that we could use as a training set local extrema, which are found by using topological optimization. If you do topological optimization, or let's say inverse design, you almost always end up with some local extremum. But when you collected several of them and then use them as a training set, you eventually could find the global extremum. And the system could start generating these similar sets of data and speed up the process of finding global extremum. This actually turns out to be very efficient. And we just, frankly, we were surprised to see how nicely it works. The next step we did in terms of machine learning is related to this so-called QUBA sampling. It is QUBA is quadratic unconstrained binary optimization. And it is well known that QUBA formalism could be applied to so-called hot, exponentially hot combinatorial optimization problems, such as optimizing traffic flow, number partitioning, travel salesman problem, and others. So what we did, actually, we developed a technique which allows mapping highly constrained continuous nanophotonics problems, such as this nanophotonic circuitry, into QUBA problem. And QUBA problem in turn is actually could be mapped to Ising Hamiltonian. You could compare these two, and they're actually the same. But D-wave machine, quantum D-wave machine, or semi-quantum D-wave machine actually works so that it's let your superconducting qubit evolve and go to the ground state, and then you just measure all these characteristics, the local fields, magnetic fields, the coupling constant, and by measuring them and then comparing to the QUBA problem, you could solve nanophotonics problem. So what we are doing now to solve our nanophotonics problem with this D-wave machine. And it looks actually very promising. So basically the idea, we use this binary variational autoencoder, which encodes continuous optimization nanophotonic problem, and we played with several of them, like thermal photovoltaics optimization, or diffraction grading, or for beam steering, and many others actually. So you convert it into binary problem, then compress the space and sample it with quantum-assisted QUBA sampler by using this D-wave machine. All right, enough about machine learning, but just in general, it's a game changer in terms of designing practical quantum photonic circuitry. So I mentioned that we recently discovered this single-photon emitters in silicon nitride. Why it's important? Because for quantum computing, as I pointed out, arguably the most promising and scalable approach is based on these photonics, because you could use this well-developed platforms. But the thing is, for that, you need this really good single photon sources, rather than just down conversion, parametric down conversion, which is probabilistic process. It increases error rate and requires way too large infrastructure. So what we obtained recently, that silicon nitride, which is a wonderful material used for nanophotonics, one can have this very efficient single photon sources. For that, we actually use slightly different way to prepare silicon nitride. Specifically, we use this high density plasma CVD growth, which followed rapid thermal annealing. And it turns out this rapid thermal annealing is very important. As a result, we found that fluorescent background was strongly suppressed, so that you would be able to see this many single photon emitters, which are bright with counts approaching, in many cases, million counts per second, stable and linearly polarized. The purity of this single photon emission is quite high, routinely below 0.2, in many cases below 0.1. Photoluminescence peak tend to be the same wavelength, which indicate that we are dealing with one particular type of defect center. And of course, this is a very well-established material platform, which could make a difference in terms of this integrated quantum photonics. So here we just show that this is like this many single photoluminescence map of this many single photon emitters. We picked up particular one and measured G2. In this case, it's 0.12. We characterized G2 for 130 meters, and actually most of them has G2 below 0.2. And it's important that we did it without any background correction or spectral filtering. So the spectrum, all this done at room temperature, it's important. Spectra look like overlap between 4 different lines, and from point to point they reproduce, meaning this is one particular type of defect. They're stable, there is no much blinking as you could see, and the number of counts approaching way above 10 to the 5 and approaching 1 million counts per second. So we already successfully integrated the single photon emitters with waveguide. So basically you excite this single photon emitter and it couples to the motor waveguide, and then you decouple with a grating and detected these single photons. This is an important slide in the following regard. So it's the key thing if you're serious about this photonic quantum computers, it's deterministically create these single photon emitters. So what we tried to do, we would fabricate many cylindrical pillars in silicon nitride, like it's shown here. And it turns out that if you optimize the size of the pillar, then actually at certain size you have, most of the pillars have actually single photon emitters. That's all very recent results. We don't have full explanation, but our working explanation, our hypothesis is as follows. Remember I mentioned that when you create this silicon nitride, you have to use this rapid thermal annealing. Because the expansion coefficient for silicon nitride and silica, SiO, different, so you create stress at the interface of the silicon nitride pillars, which are sitting on silica substrate. And at certain stress, it results in a single photon emitter. It's stress induced, but that stress depends on the size of your pillar. So by choosing the right size of a pillar, you actually create only one single photon emitter. Here we just picked up arbitrary 17 pillars in a row, and all of them show anti-bunching, all 100%. And actually more than 50% have G2 going below 0.5. It's actually very important because all other ways of create single photon emitters, they are statistical, like this implantation or annealing. They're statistical, meaning that they are described by Poisson distribution, meaning that there's like 35% of single photon emitters, the rest are either zero emitters, zero photons or more than one photon. Here it's clearly above 50%, which means that potentially it could be optimized so that the yield could approach 100%, meaning that every pillar would have just one single photon emitters. And that could make a difference from this photonic-based quantum computing, which is the final goal. So let me then briefly mention yet another activity, because so far I was talking about this photonics-based quantum applications, but we're also part of this Quantum Science Center supported by DIE. It's a big effort. And in this effort, we try to bring together different degrees of freedom. We use spin qubits for memory. And these spin qubits, like the nitrogen vacancy, for example, has spin qubit, could be initiated and controlled with microwave photons. They're around like 3 gigahertz range. If you place them on top of magnetic field, which supports magnons, the different spins could couple, different qubits related to these spins could couple via magnons. And qubits could be read out with optical photons that could include this plasmonic enhancement and speedup, which I was talking about. And most importantly, this magnon coupling between qubits could be controlled electrically if you place them on ferroelectric substrate. And that's what we recently demonstrated. This is a little bit busy slide, but the idea is actually simple. You have this magnetic film, COFIP, on top of this ferroelectric substrate. And you have spin, nitrogen vacancy spin on top of this magnetic field. So when you apply voltage, you create stress in your ferroelectric substrate. This stress converted to the change in magnetization of magnetic field. And when you apply voltage and change the magnetization, as a result, the magnon band as a whole moves. So let's say if initially the magnon band was above the resonance of your electron spin, then basically there is no much coupling between electron spin and magnons. But if you now apply voltage and move the magnon band, then now the spins start to interact with each other via these magnons. So you could switch on and off your interaction between qubits by basically applying voltage. And you read it optically by looking at the relaxation time. And indeed, we showed when there is no coupling to magnon, then the relaxation is slow. And when there is a coupling, then the relaxation is fast, indicating that there is very strong spin-magnon coupling. Of course, you could invert this problem and say, hey, the electrical field control, let's say, this relaxation time, but what if, could I, by measuring this relaxation time, define what is the electrical field which caused it? But for that, you would like to have a sharper resonance. For example, you could pattern your magnetic field that supports magnons, collective spin excitations, so that the resonance would be sharp, like it's shown here. And we showed that in this case, you could use this magnon enhanced sensor to detect electrical field with record high sensitivity, which is 2 orders of magnitude higher than the one used with conventional NV centers. So that's kind of the approach which will involve magnons, local spins, photons, microwave photons, and optical photons for more complex quantum system, which could be used as quantum repeaters, quantum sensors, and so on and so forth. So let me wrap up and show that the basic idea of using plasmonic metamaterials, non-antennas, arrays of them, is actually to speed up quantum processes, such as the single-photon emitters, so that they would be faster than decoherence process. I illustrated this idea by using an example of this production of single photons, but the same idea could be applied for single photon detectors, for quantum frequency converters and deterministic gates. It seems to be a very general approach by confining electromagnetic modes in exceptionally small volumes, speed up quantum processes so that they would be immune to decoherence, even at room temperatures, ideally. And I also made the point that for complex photonic integrated circuitry, it's very important to imply machine learning, because otherwise it's just simply not feasible. And we demonstrated the power of machine learning for a number of quantum applications, including this metrology, quantum device optimization, and even quantum super resolution. All right, let me end up with this outline, which would remind you what we discussed, and I'd be happy to answer your questions now. Thank you.
Thank you very much, Professor Shalaev. So now we have time for questions. So any question, you can just open your microphone and ask it. And if you don't have a microphone, you can simply write it in the chat and I can read it. So just come to ask your question. I cannot see all the faces nor the hands being raises.